In this video, we're going to talk about a neuron and neurotransmission. So essentially, a neuron is the basic unit of the nervous system. And neurotransmission is the concept of how one neuron has the ability to communicate with neighboring neurons. So I first want to talk about the major structures of this cell. So much like other cells in the human body, there is the soma, or the cell body. And within the cell body is the nucleus. This is where the DNA is housed. What distinguishes a neuron from other cells, however, are these other structures. So first and foremost, we have dendrites on the left and terminal branches on the right. These are these filaments, these fibers on either end of the neuron. And dendrites, importantly, receive information, and terminal branches send information. And that's important because information on a neuron only travels in one direction. In this case, obviously from left to right, since dendrites receive information and terminal branches send information. So it's only in one direction. The long fiber in the middle is called the axon. And an axon can be extremely long. For example, there are some neurons that stretch all the way from our spinal cord to our big toe. So you can have axons that are multiple feet long. And then pictured here is a yellow fatty substance called myelin sheath. And this is a substance, like I said, made of fat, and it serves as an insulator. Essentially, it speeds up the communication process known as neurotransmission. And not all neurons have myelin. So basically, only neurons that need to communicate quickly are going to have myelin. As an example, imagine you touch a hot stove. You're going to pull your hand back immediately without even thinking about it. So you can bet that the neurons in the arm and the arm muscles, for example, are highly myelinated. But on the other hand, something like digesting your food, there's also neurons that are regulating our digestion, and digestion does not have to happen immediately. It doesn't have to happen extremely quick, so those neurons are probably not myelinated. The body is extremely efficient. The body does not want to waste any energy creating myelin if it's not necessary. But as one more example, if you practice a task and get better and better and better at it, like imagine you're a musician and the first time you pick up a guitar, you're not very good, but years and years go by and you can play that instrument very well, the muscles and the parts of the body that are involved in playing that instrument, the neurons controlling those body parts get myelinated over time. All right, so the last structure that I want to focus on is the little spaces in between the myelin, and they're known as nodes of Ranvier. Importantly, we're going to consider those as recharging stations, and that'll become important later. All right, so here are the basic structures of a neuron, and now we have to talk about how a neuron communicates with other neurons through a process called neurotransmission. So basically, a neuron is extremely simple in the sense that it has one job, and it either does that job or it doesn't do that job. What I'm referring to is an action potential. So think of a neuron like a gun. A gun either fires or it doesn't fire. So, imagine this is a gun, the gun is resting, and then I pull the trigger, and then all of a sudden the gun fires. That's what we're talking about when we say action potential. And specifically, neurotransmission is an electrochemical process. There's electricity involved, which we'll describe in a moment, and there are chemicals involved. And the idea that the gun either fires or it doesn't fire is known as the all or none principle. In other words, again, going back to the gun analogy, you cannot pull the trigger halfway and have the gun fly half as fast. It doesn't work like that. You either pull the trigger and the gun fires and the bullet flies, or it does not. So it's all or none. Very simple. Yes or no. It's binary. And, a quick side note, it's fascinating to think that all of the complex thoughts and behaviors that we have, they all boil down to individual cells that either do their job or don't do their job. It's very, very simple and binary on some level. All right, so let's get a little more detailed into the process of neurotransmission. If we focus really closely in on the terminal branch of one neuron and the dendrite of another neuron, if we focus really closely there, it might look something like this. And what we see here is that neurons do not actually touch one another. They are separated by a small space called the synapse, or the synaptic gap. And in this drawing, anyway, there are these small dots known as neurotransmitters. At least this is an artist rendering of neurotransmitters. So neurotransmitters are the chemical substances that allow information to be released from one neuron and absorbed by another neuron. There are a number of neurotransmitters, many of which you're probably familiar with. For example, most people are familiar with dopamine. That's the feel-good chemical. It boosts our mood, for example. It makes us feel pleasure. All right, so let's go back to this drawing for a moment. And what I simply want to describe is the electrochemical aspects of neurotransmission. So you are responsible for really understanding the two basic processes here. So let's start off with the chemical aspect. So chemicals, as we've already described, are known as neurotransmitters. So imagine this cell's job, one of its jobs is to produce dopamine or serotonin or other neurotransmitters. These chemicals come in two forms, excitatory and inhibitory. So excitatory chemicals are saying go, go, go. And inhibitory chemicals are saying stop, stop, stop. So this next neuron is receiving all of this information. And I should mention that each neuron is capable of connecting or communicating with up to 10,000 other neurons. So if we have billions of neurons in the nervous system, and each can connect up to 10,000 other neurons, we're talking about an extremely complex network. But right now we're trying to obviously simplify the process, focusing on just the connection between a few neurons. So imagine this neuron over here is currently receiving chemical information from neighboring neurons. And some of these incoming messages are excitatory. They're saying, go, 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 hit the accelerator. But other neurons are inhibitory. They're saying, stop, stop, stop. So what should this neuron do? Should it rest? Should it remain in a state of what's called polarization? Or should it fire? Well, every single neuron has a threshold. The threshold is important because it's basically this point where you can have these excitatory messages saying go, go, go. But if there's not enough of those messages, in other words, if it's not at that threshold, the neuron doesn't do anything. Again, going back to the gun, if you don't pull the trigger hard enough, nothing happens. But eventually, if you increase the pressure, eventually you get to the point where the trigger is pulled and the bullet flies. That is what we're talking about with a threshold. So you have to have enough excitatory incoming messages to cause the gun to fire, or in other words, to create an action potential. All right, so imagine that the threshold is reached. There's enough excitatory information relative to inhibitory information. That point is reached. This is where the electricity part comes in. So when a neuron is at rest, there are two important molecules that play an important role in the electrical aspect of an action potential. And those molecules are sodium and potassium. These are molecules that carry an electrical charge. And what's important, obviously there's a lot more detail to this, but we're just covering the most important concepts here. What's the most important thing to consider is that sodium is more positively charged than potassium. And when a neuron is resting, when it's not doing much, there's more sodium on the outside compared to on the inside. There's more potassium on the inside. So again, we're looking at this neuron right here. Right now it's just resting. So what we would expect is a bunch of sodium on the outside and a bunch of potassium on the inside. But that threshold was reached. All those excitatory messages came to this neuron and said, go, go, go. And this is where the magic occurs. When the threshold is reached, a sodium-potassium pump opens up. Think of it basically as a gate. The gate opens up, and when that occurs, that allows more sodium to rush inside the cell and some potassium to leave. So what occurs as a result is more of a positively charged ratio inside the cell. More positive means, there's an electrical current. So we actually get a wave of electricity originating in the cell body and traveling down the axon. And if it reaches the terminal branch, that'll cause the release of its own chemicals, which are either excitatory or inhibitory, to then impact neighboring neurons. So that is the gist. Basically, we have the chemical component, which is the neurotransmitters. They're excitatory or inhibitory. And then we have the electrical part, which is the sodium and potassium. When the neuron is having an action potential, more sodium is rushing inside, potassium is leaving. The textbook also describes other chemicals that are involved, but for the purposes of Psych 1, sodium and potassium is what we want to be focusing on. So I just want to cover a couple more aspects that are important to kind of fill in the gaps here. The first is going back to the concept of nodes of Ranvier. Earlier, we talked about the idea that these are a recharging station. And essentially what they are is sodium-potassium pumps. So think of the idea that what begins here is a wave of electricity. A wave, that's important. So imagine you're at the beach and you're sitting at the shore and you're looking out at the ocean, and what you see is a giant wave forming. And it's gigantic, but by the time it gets to the shore and it gets to your feet, it's tiny. Because what occurs is that wave dissipates. In other words, it gets weaker over time. Any wave is going to get weaker over time unless something occurs. And that's a problem, because if the wave of electricity is not strong enough, by the time it gets to the end of the neuron, it won't trigger the release of those neurotransmitters. So as a result, these nodes of Ranvier, they will increase the electrical charge. They'll allow more sodium to come in and make sure that that wave of electricity remains really, really strong enough to release neurotransmitters and therefore impact neighboring neurons. Okay, so the last thing I want to cover in this video is, how does this process stop? How does it cease? And there's a number of processes. For example, enzyme deactivation is one that's described in the textbook, but the most important one, the one that's focused on mostly, is called reuptake. Reuptake is basically a recycling program. So again, imagine a neuron releases neurotransmitters into the synapse. Typically what happens is that this neuron releases more than is necessary. But as we're going to see in this chapter and in many chapters, our body is extremely efficient and it does not like to waste anything. So the process of reuptake is where extra neurotransmitters can actually be reabsorbed by this neuron and used again later. And when that process happens, the action potential stops. So neurotransmission ceases to occur after reuptake. And the reason I like to focus on that is because this understanding has helped us with pharmaceutical drugs. So for example, Prozac, which is one of the most commonly prescribed antidepressants, and that falls under the category of SSRI, which stands for Selective Serotonin Reuptake Inhibitor. So serotonin, is a neurotransmitter. And when people take Prozac, what's interesting is it doesn't give you more serotonin. What happens is it prevents serotonin from being reabsorbed, or it stops the process of reuptake. So SSRI, again, stands for selective serotonin reuptake inhibitor. So if somebody has depression, obviously one of the most important symptoms of depression is deflated mood. So when you take Prozac, again, it doesn't give you more serotonin, but it allows your body to use your serotonin longer because it doesn't get reabsorbed by those neurons. It stays in the synapse longer, and therefore it can have a greater impact on neighboring neurons, increasing one's mood. In review, this video covered the basic structures of the neuron and some information about neurotransmission, the electrochemical process that brings about the ability for one neuron to communicate to other neurons.